Assalamu alaikum. Am I audible?
Alaikum assalam, sir. Yes, sir, you're audible.
Yes, sir, you're audible.
How are you all?
Good, sir. Alhamdulillah. How are you?
Alhamdulillah,
Sir.
fine.
How are you?
Khalid, you was not there in last class.
Sir, I went out that day.
Okay. Anything special or just for fun?
No, sir, I went with my family out.
Okay, okay.
Fireworks happening that day.
In last class, I defined stress strain curve for which we have defined these three terms. Let me give you a question related to this part. Suppose this is stress and this is corresponding strain. Let's say the substance is A. The substance is B. So you'll be asked, from the graph, define which is more elastic in A and B, which is more ductile, and which is more brittle. Try to define. Good, Khalid. Next. Good, Khalid. Hamza, you got any answer?
Yes, sir, giving the answer.
Okay. Good, Salman. Good. Hiba,
Yes, sir.
just tell me, how do you define stress strain curve for elastic behavior of particular material? In last class, I defined you a stress strain curve and its various significance. Just say this particular curve from O to A is elastic limit up to which Hooke's law will be valid. So you'll say stress and strain in this particular part will be directly proportional to each other. So up to this region, if you define or if you calculate slope of this particular curve, it will define you modulus of elasticity and which defines simply elastic behavior of particular material. Okay.
Yes, sir.
So in this particular graph, Hamza, just tell me which one having greater slope.
Sir, A.
So which one will be more elastic?
Sir, A.
Good. How do you define ductility of a particular material related to a stress strain curve? By knowing its plastic region or length of its plastic region. Okay. Hiba, just tell me which one have longer plastic region, A and B?
Sir, B.
Good. So B will be more ductile. And for third part, brittle nature, it should be less plastic region or a smaller plastic region. So for A, having smaller plastic region, so it will be more brittle. Is it clear? Hamza?
Yes, sir.
Yes, sir.
Okay. You all have written? Hamza,
Yes, sir.
done?
Yes, sir. Done.
Yes, sir, done.
Okay. Next topic in this particular chapter is potential energy stored in a particular wire. Suppose you have a rod hang vertically from any rigid support having length L. Area of cross section A. Now, if you apply any deforming force on this end to stretch it, deformation in this particular wire, let's say, is up to this part. It means total elongation in wire is up to this. small l. But this deformation in this wire must be achieved in some step. Let's say in last part, deformation is dy, and from this point to this point, deformation is y. Is it clear? I've just assumed the last extension in this particular wire is dy and rest of all is just y, so that the total elongation in this wire is L. Hiba, is it clear?
Yes, sir.
Consider a wire having length L, area A. So we can define, according to Young's modulus, y equals to force times length divided by area of cross section times extension y. So from this we can write F equals to y A divided by L times y. We may relate this particular expression in terms of a spring as for a spring F equals to K times X if you are using external force. In terms of restoring force, it will be minus of K into X, where X is displacing the spring and K is called spring constant. Similarly, in this part, Y is extension in this wire and rest of the term is constant. So we can relate these two expressions. Then K equals to YA divided by L. So from this, we can say spring constant will depend upon area of cross section and length. I will use this particular formula to define a spring constant and its various impact in oscillation and wave, second last chapter, okay?
Okay, sir.
Now, this much amount of force having extension y, if you have to extend further by dy, we must need some external work done to this particular wire. So let's say dw amount of work is done to stretch by dy. So work done equals to force times displacement. Put the value of F, so it will be YA divided by L times y into dy. Now integrate this particular expression. This amount of work done is against the elastic behavior of rod. So this work will get converted into potential energy. I define you what do you mean by potential energy. So whenever there is work done against any conservative force, gravitational, electrostatic, and elastic, this work get converted into potential energy, or you can say stored potential energy. Similarly, in this part, since wire behaves elastic, so it will have some elastic factor or elastic potential energy or elastic behavior. So this work on integration will become potential energy stored. YA divided by L is constant. We have y to the power 1. So on integrating, it will be y squared divided by 2. Now, limit of extension. Since wire is initially at this point, when value of y will be 0, last extension is up to this, so y will become L. So if you put the limit from 0 to L, So it will be from 0 to L. So YA divided by L into 2, upper limit L square, lower limit 0 square. So potential energy in this wire will be half YA divided by L times L squared. Salman, is it clear?
Yes, sir.
Hamza, any doubt?
No, sir.
Okay, just write it down. Hiba, you have written?
Yes, sir. Done.
Salman, done?
Yes, sir. Done.
Now, we have to transform this particular relation in terms of force and extension only. So let me define you. Potential energy equals to half YA divided by L times L times L. Since Y is approx equals to L, so we can write force equals to YA divided by L times Y equivalent to YA by L times small l. So this particular part will be force and this particular part will be extension. So we can write it as half force into extension in this particular wire will be equals to potential energy stored. Hamza, is it clear?
Yes, sir.
Next, we can write or we can transform this particular formula in terms of stress and strain as well. Potential energy equals to half force times extension. Now, if we divide this term by volume and multiply this term by volume, so there will be no any effect by multiplying and dividing by same quantity. Now, force times length divided by volume, we can write it as A times L into volume V. Now this part and this part will be nothing but force over area. So it will be stress, delta L by L, or deformation by its actual length, strain. So we can write it as half times stress into strain into volume equals to potential energy stored in wire. Salman, is it clear?
Yes, sir.
Okay, just write it down. Let me give you a problem related to this part. A wire having dimension 4 mm square cross 2 meter get expand by 2% on applying stress. If Young's modulus is 2 into 10 to the power 11 Newton per meter squared, find potential energy stored. Hamza, what do you mean by expansion of wire by 2%?
Sir, the bulk modulus?
No, simply if you are if in this particular question it is given percentage change in length, since it is expanding along length, so it will be percentage change in length. And how we calculate percentage change in length? So it will be delta L divided by L into 100 equals to 2%. So we just need only delta L by L. So it will be 2 by 100. And this particular fraction is also called strain. Is it clear?
Yes, sir.
Now we have Young's modulus y equals to 2 into 10 to the power 11 Newton per meter square. We can find volume related to this part, area of cross section and length. Now use the above formula and try to find for potential energy. Try to solve. Hiba, any problem solving?
No, sir.
Hamza, you got any answer?
Not yet, sir. I'm doing.
Let me define you how to simplify it in more easy form as potential energy equals to half stress into a strain times volume. So for using this part, we must need a stress. So one way is to find a stress using Young's modulus and strain. Other way is to define Young's modulus equals to stress divided by strain. So we may transform this equation to get stress as y times strain and put this value in this part. So you'll get half y strain squared times volume. Now we have Young's modulus, strain, and volume. Put these values and simplify it. Hamza, is it clear now?
Yes, sir.
Khalid, you got any answer?
Yes, sir. Still calculating.
Let me solve. Half Young's modulus is 2 into 10 to the power 11. The strain we have 2 into 10 to the power minus 2, or you may write it as 2 divided by 100. So 2 into 10 to the power minus 2. On squaring, it will be 2 into 10 to the power minus 2. Volume is 4 mm square. So it will be 4 into 10 to the power minus 6 times length 2. So this 2 and this 2 will cancel out. Now we have this 2 and this 2, this 4 as integral part. 2 into 2, 4, 4 into 4, 16 into 2, 32 into 10 to the power plus 11, minus 2, and minus 6, minus 10. So it will be just plus 1. So you may write it as 3.2 into 10 to the power plus 2 joule. I think this was just two-step problem. Hiba, is it clear?
Yes, sir.
Was it so difficult to simplify?
Oh, sir.
Then why you all have taken so much long time? Okay. Salman, is it clear?
Yes, sir. I was about to send the answer.
Okay. Okay. You all have written?
Yes, sir.
Now, related to this part, let me define you some more topic. One of the term will be Ozone's ratio. Suppose you have a rod attached to any fixed support having initial length L. On applying any deforming force on extension, there will be decrease in its width. So on expanding, initially diameter of this particular rod was D, but now on stretching, it will become D minus delta D. Extension is from this point to this point, let's say delta L. So in this part, we have two different types of deformation. One is along length and the other is along its width. So we may define two different deformation. First is longitudinal, that is along its length. So it will be delta L divided by L. And next is along its width, which is also called lateral. So lateral strain will be equals to change in diameter divided by diameter, or we can write it as change in radius divided by its initial radius. Now, since width or radius is decreasing, so final radius will be smaller as compared to its initial. Similarly, final diameter will be smaller as compared to its initial. So there will be some negative sign at this point. Now, if you take the ratio of these two deformation for the solid, it is called Poisson's ratio. So Poisson's ratio equals to lateral strain divided by longitudinal strain. Poisson's ratio is represented by sigma. Lateral strain is delta D divided by D. Longitudinal strain is delta L divided by L. Or it may be written as delta R divided by R, delta L divided by L with negative sign. Hamza, is it clear?
Yes, sir.
Will there be any unit of this particular ratio, or it would be in unitless? Hiba will answer. Hiba, tell me. Just see this particular part. It is ratio of length to its original length. Both having same unit, so they will cancel out. So for this longitudinal strain, it will be unitless quantity. Similarly, for lateral strain, diameter, and this is also diameter, both will be measurement of length. So unit will get cancelled out. So it will be again unitless quantity. And the ratio of two unitless quantity, that is Poisson's ratio, will also be unitless term. Is it clear?
Yes, sir.
So this particular quantity will be unitless. Now, you will be asked to define for perfectly rigid body. For rigid body, there will be no change in its length, no change in its volume. So Young's modulus, shear modulus, bulk modulus will be infinite, but Poisson's ratio will be of just 0.5. In general, sigma lies in between this. This is theoretical value, and this is practically calculated. Salman, any doubt?
No, sir.
Okay, just write it down. Hiba, done?
Yes, sir, done.
Okay. Next is elastomer. You must have used thermocol for various school projects. Hamza,
Yes, sir.
what is the main use of thermocol?
Sir, for charts or something?
Okay, for the stationary thing?
Yes, sir, like in school, mainly that is used for it.
Okay. Let me define with some other use. Suppose for carrying any object, let's say any electrical gadget, computer, television, fridge, AC, washing machine, anything. If you transport one place to other place, there will be use of thermocol to protect it. You must have seen somewhere.
Yes,
Yes,
sir.
sir.
So the actual use of thermocol is there. Thermocol is called elastomer. What do you mean by elastomer? The substance which having only elastic limit. Suppose if you start compressing thermocol, it will get compressed up to a certain limit. And if you release it, it will remain or it will regain its original shape exactly. Okay. But if you compress it a little bit more, it will get broken. It means the substance which having only elastic limit beyond which it will get broken is called elastomer. So what will be use of it? So you can say it will be best shock absorbing substance. So it will be helpful in carrying those electrical gadgets and protect it from any injury during traveling. Okay.
Yes, sir.
So let me define you its variation with stress. On compressing or on applying stress, it may follow this path to reach some limit, let's say up to this point. On releasing that deforming stress, it may follow this path to regain its original shape. This particular point is the maximum limit or the maximum amount of stress withheld by it without breaking. So this is called saturation point. So we can define elastomer, the substance having elastic limit only beyond which it would break. Its main use is to absorb shock during traveling. So it is used as shock absorbing material during transportation of goods. So this related graph will define you its absorbing tendency. Greater the area of this particular graph for a particular material, it will be good shock absorber. So we can say greater the area of stress strain, it will be good shock absorber. Is it clear?
Yes, sir.
Hiba, any doubt?
No, sir, no doubt.
Okay. Since in this particular graph, a rate of increase and rate of decrease for stress and strain is not the same. Let me define you. Suppose if you draw horizontal line. So on expansion, strain is up to this part, but on contraction, strain is this. So we can say a stress and a strain is not going along same rate for both extension and compression. There will be some lagging with respect to one another. This behavior of material is called hysteresis. Since we are defining for any particular object, so this hysteresis is also called mechanical hysteresis. Hysteresis is lagging behind property. For this case, we can define the lagging behind tendency of stress with respect to strain or vice versa on expansion or compression. Is called hysteresis. Khalid, is it clear?
Yes, sir.
So related to this term, you will be given two different curves for which one of curve will be thin and the other will be thick, and you'll be asked which of these two substances will be good shock absorber. So just relate this particular statement and say more the area of this particular curve, it will be good shock absorber. Salman, any doubt?
No, sir.
Okay. You all have written?
Yes, sir.
Salman, done?
Yes, sir, done.
Okay, so this is all about mechanical properties of solid. Let's start new chapter, that is mechanical properties of fluid.
Sir, that mechanical hysteresis was the final part?
Yeah,
Oh, okay.
First, what do you mean by fluid? So we can say the matter which having tendency to flow is called fluid. Matter having tendency to flow. That is both liquid and gas. For this particular fluid, we first define density. Density is simply ratio of mass and its occupied volume. So we can write it as mass of substance divided by volume it would acquire. Density of water at 4 degrees Celsius will be maximum and equals to 10 to the power 3 kg per meter cube. In terms of CGS unit, it will be 1 gram per centimeter cube. Now we can define another term related to this density, relative density. You must have learned about this in class 9th. Relative density is simply ratio of density of any substance with respect to density of water at 4 degrees Celsius. So it will be density of any substance divided by density of water at 4 degrees Celsius. This particular ratio is also called specific gravity. Since in this particular part, we are taking ratio of same quantity, so it will be unitless term. Is it clear? Hiba, any doubt?
No, sir.
Okay. So for this entire fluid, we mainly divide into two parts. First is hydrostatics and second is hydrodynamics. Hydrostatics means fluid at rest. So a study of fluid at rest is called hydrostatics. Study of fluid at rest. So in this part, first we define pressure due to liquid, Pascal's law and its various application. Second is Archimedes principle. Third is surface tension. Similarly, hydrodynamics, study of fluid in motion. So first will be viscosity, for which we may define different types of flow. Next, and the most important part, Bernoulli's principle and its various application. Okay, just write it down till this part. Then I'm starting with first hydrostatics. You all have written?
Yes, sir. Done.
Khalid, done?
Yes, sir. Done.
So let's start with pressure. Suppose you have a surface on which we may apply force, one along this direction, let's say F1, and the other along this direction, let's say F2, and one along this direction, let's say F3. So related to its inclination, we may define a term that is called thrust. You must have learned about this word in class 9th. Hiba, do you have any idea what do you mean by thrust? Salman, yes?
Sudden push or something.
Sudden push or sudden pull?
Yes.
No. Just see in these three different forces. Which of the forces normal to the surface?
One.
If one is acting normally to the surface, just see again.
F3.
Normal means perpendicular to that surface. F3 is acting tangential to it. So it will be parallel to the surface. This F2, which is perpendicular to it, okay? So thrust is basically perpendicular force acting over that particular surface. Perpendicular force acting on surface is called thrust. So on the basis of this thrust, we may define pressure as the thrust acting on surface per unit area of impact is called pressure. So pressure is thrust divided by area of cross section. Thrust is nothing but perpendicular force. So it will be force divided by area of cross section. So SI unit is Newton per meter square, or we can call it as Pascal PA. And it will be scalar quantity. Salman, is it clear?
Yes, sir. Wait a second. I'm right.
Just write it down. Suppose a force of 20 Newton is required to inject a pin on surface if area of tip is 40 mm square. Find pressure exerted. We have force, area of cross section. Just put these two values. Hamza, 1 mm square is equals to 10 to the power minus 6 meters squared. Salman, you got any answer?
No, sir. I'm in calculation.
We have force as 20 Newton, area of cross section 40 into 10 to the power minus 6. So 20 in 2 times will be equals to 40, or you may write it as 0.5 times. This 10 to the power minus 6 on moving to numerator, it will become 10 to the power plus 6 Pascal. Good, Hamza. Khalid, is it clear?
Yes, sir, I got the same answer.
But you haven't sent to me.
Sir, I was going to say it till then you wrote the answer.
Okay, okay. Now we have to basically calculate pressure exerted by fluid. So let me define you pressure due to column of liquid, which is also called gauge pressure, represented by PG. Suppose you have a container or a vessel in which there is liquid up to this point. Consider liquid having density rho in a vessel at rest. Okay, Hamza, will the particle of this particular liquid at this state be in rest or in motion?
Sir, they will be in motion.
Okay, why it would be? Khalid, why the particle of this particular liquid will be in motion?
Sir, I didn't get you.
Why the particle of this liquid kept in vessel is in motion?
Sir, because there is space between the particles, so they will.
No, just say, since we are in room temperature, which is more than 0 Kelvin. So every particle having greater temperature or a temperature having greater than 0 Kelvin will have some thermal kinetic energy. So they will be always in motion. So due to its motion, they will exert some pressure on side wall as well as bottom or for this entire part. But we are considering pressure due to this particular fluid as accelerated by gravity. So for this, let's assume a cross-sectional part in shape of cylinder having area this A and height of this particular strip H. And since this particular amount of fluid will accelerate in downward direction due to its gravity, so they will exert some pressure on this particular surface. Okay, this pressure due to this column of liquid is called gauge pressure. Okay.
Yes, sir.
So for pressure, we must need two different parts, force and next area of cross section. So mass of liquid equals to density into volume density is rho, volume is area of cross section into height. Is it clear? So this mass will exert some force due to acted upon by gravity. So force exerted will be equals to mass times gravity. Mass is rho ah times gravity. So we can say pressure equals to force exerted over area of impact. Force is rho ah times gravity divided by area. So A and A will cancel out. So you'll get rho GH. In this expression, we have gravity. It means this column of liquid would be accelerating towards downward due to gravity, due to which it must be generating some pressure at its this portion. Is it clear?
Yes, sir.
Hiba, any doubt?
No, sir.
Now, in this expression, rho GH, rho is called density of liquid. G is net acceleration. H is vertical column of liquid. So you'll be asked if this entire system is allowed to fall freely under the effect of gravity. So what will be gauge pressure in that case? So you say net acceleration for free falling body will be 0. So if you put this net acceleration in this expression to be 0, you will get net pressure exerted will be 0. Okay. Hamza, is it clear?
Yes, sir.
So this gauge pressure is basically due to acceleration of liquid due to gravity. Now in this part, we have only these three terms. So we can say this gauge pressure is independent of direction of impact. It means at same depth, h, it will act equally in all direction. Next, there is no any information in this formula about amount of liquid. So we can say gauge pressure will be independent of amount of liquid above it. It just depends upon vertical column above it. So from this we can say it is independent of direction, or we can say it acts equally in all direction at same depth. Next, it is independent amount of liquid. It just depends upon vertical strip placed over it and nothing more. Hiba, any doubt?
No, sir, no doubt.
Okay, just write it down.
Done, sir.
Salman, you have written?
Wait a second, sir. Done. Sir, done.
Okay. Now let me define you some property related to this statement. You'll be asked, suppose you have a vessel in which liquid is filled up to this point. So at same depth, let's say from this point to this point, H, if you draw a horizontal line, pressure P1 is along this direction, P2 is along this direction, P3 is along this direction, and P4 is along this direction. So you'll be asked, what would be the relation between P1, P2, P3, P4? So you'll say, at same depth, pressure in all directions will remain equal. It will be independent of direction of action. So you'll say P1, P2, P3, and P4 will be equal to each other. Khalid, is it clear?
Yes, sir.
Similarly, next question will be, suppose you have connecting tube, which may have different shape of vessel connected together. Like this. So if you start filling liquid from any one side, so level of liquid raised in each vessel will remain same. Like this. So let's say depth H, pressure at this point is P1, at this point P2, P3, P4, and P5. Salman, just tell me, in which of these vessel would contain maximum amount of liquid? First, second, third, fourth, fifth. Hiba, just tell me. In which vessel do you think having most volume of liquid?
Sir, all will be same.
I'm asking about volume of liquid, amount of liquid.
Oh,
You say in first or second, okay? But since pressure at same depth, H, if you calculate, it will give you same result. So P1, P2, P3, P4, and P5 all are equal to each other. So we can say pressure at any particular depth will be independent of amount of liquid. It just depends upon vertical column above it and nothing more. Hamza, is it clear?
Yes, sir.
Okay, just write it down. You'll have written.
Yes, sir.
Salman, done?
Done, sir.
Okay. On the basis of this part, gauge pressure, let me define you the concept of atmospheric pressure and how to calculate its value. First, tell me, do you have any idea what do you mean by atmospheric pressure? Khalid,
Yes, sir.
what do you mean by atmospheric pressure?
It is the pressure exerted by the atmosphere.
Good. Or you'll say pressure due to air column. Now, for this part, we have to calculate its numerical value. For this, in a vessel, mercury is filled up to this part. Now, if inverted evacuated capillary tube is inserted into it, capillary tube or very thin tube, which is initially evacuated. It means there is no air inside it. Now it is placed into this particular bath like this. Now suppose a point this A and another point this B. Hamza, just tell me, will the pressure at A and B equal or different?
So different.
Why?
So because A will be in open air, but B will not be in open air, so the pressure will be different here.
Good. So you'll say there is air above at A, which is exerting some atmospheric pressure. And since there is no any particle above at this particular point P, so there will be no pressure at P. Okay. So we can say pressure at B will be 0. Okay. Next, Salman, will there be movement of fluid from A to B? Since B having lower pressure or less pressure as compared to A, so will there be any movement of fluid from A to B, or it will remain as it is? Hiba, any guess? Let me define you. For any pressure difference, just as this part, we have pressure difference between A and B. So matter will flow from higher pressure to lower pressure. So in this part, we have A at higher pressure, B at lower pressure. So this mercury will start rising up in this B to create some pressure at B such that pressure at A and pressure at B will become equal to each other. Is it clear?
Yes, sir.
So experimentally, it was calculated total vertical column of liquid is about 76 centimeter height in case of mercury. So we can say at equilibrium means net pressure becomes equal. So pressure at A, pressure at B equals to each other. So it will be due to the vertical column of mercury. So gauge pressure, rho GH. Now put the value of rho in case of mercury, density is 13.6 into 10 to the power 3. Gravity is 9.8 and vertical column is 76 centimeter. Divide by 100 to convert into meter. Now, if you simplify this particular expression, you will get 1.013 into 10 to the power 5 Pascal. This pressure is equals to atmospheric pressure at sea level. So it is also called 1 atm. Salman, is it clear?
Yes, sir.
Okay. There will be some other unit for this particular pressure, or you may write this particular term as 76 centimeter of Hg. In this expression, it means the pressure exerted by 76 centimeter of column of mercury will be equivalent to 1 atm. So there will be some expression which pressure will be given in terms of its vertical column. So you may convert using the concept of gauge pressure into normal pressure. Okay. Hamza, any doubt?
No, sir, no doubt.
There will be some other unit for this particular pressure. One is bar. 1 bar equals to 10 to the power 5 Pascal. 1 millibar, 10 to the power 2 Pascal. 1 torr, defined by torricelli, which is equals to pressure exerted by 1 mm of Hg. So it will be equals to 133 Pascal. Just write it down to this part. Khalid, any doubt?
No, sir.
Done, sir.
Okay. You may perform this particular experiment to know, is there any flow of liquid in this particular tube or not? Take glass, transparent, water in a particular container or vessel. Place a burning candle on the surface of water and just cover this particular burning candle from glass. And sometime when all of oxygen inside glass will burn out due to flame, level of liquid start rising up in that glass. It means on burning oxygen, pressure inside the glass will decrease and will tend to move level of liquid rise up to create some pressure from inside. Okay.
Well, the candle should be in the water.
Place your candle, let's say in shape of some cylindrical shape of about this type, just like Diwali candle. Place it on the surface of water and just cover it by any glass so that there will be no escaping of air from this part. So this candle will burn up to where till there is oxygen inside it. So when whole of oxygen burn out due to this flame, this will stop burning, and in that case pressure inside it will get decreased, due to which there will be a rise in level of liquid from this part. You may do this part at your home if you want to. I'm not forcing to do, and all it's your own risk. Okay. Now we have two different types of pressure. One is called atmospheric pressure and the other is gauge pressure. So if you combine these two together, so it will be called as absolute pressure. So absolute pressure equals to sum of atmospheric pressure and gauge pressure. So P absolute equals to P naught plus Pg. Now let me give you some problem related to this concept. Find gauge and absolute pressure at depth of 10 meter below an ocean. Take density of water is 10 to the power 3 kg per meter cube and gravity is 10 meter per second square. Try to find good Khalid. Hiba, just send me your answer. Just put the value of all these three terms and simplify it. Then put the value of this and simplify. Nothing more. Good, Hamza. Good, Hiba. Salman, just send your answer. Density of water is 10 to the power 3, gravity is 10, and height or depth of liquid is 10. So on solving, you will get 10 to the power 5 Pascal. Now put the value of atmospheric pressure and gauge pressure and simplify it to get absolute pressure. Atmospheric pressure is 1.013 into 10 to the power 5 Pascal. Gauge pressure is 1 into 10 to the power 5. So take out 10 to the power 5 as common. So you're left with 1.013 plus 1. So in total, it will be 2.013 into 10 to the power 5 Pascal. Salman, is it clear?
Yes, sir.
Okay, so do you have any doubt till this part in fluid? Is everything clear? Hamza?
Yes, sir.
Good. So just revise this entire part and do problems related to gauge pressure and absolute pressure. In next class, I will define you different application of this particular pressure, and then we'll start Pascal's law. Okay.